Off we go. All right, so hi everyone. Thanks for having me. I'm going to give you an introduction to what you can do with the Julia language in the context of processing and analyzing ocean color data and Earth observations more generally. In the presentation, I will change slides. Oh, let's see. The presentation will proceed in four sections, mostly three. The first one, I will just introduce the Julia language briefly for those who might not be familiar with it, and sort of the notebooks and environments that we will use. Then I will talk about ocean color data more specifically. And in the third section, I will sort of broaden the scope a little bit to Earth observation more generally. Each of the sections will have notebooks that will be linked into the presentation, and I will demonstrate them on the screen. You will be able to use them afterwards, hopefully. And so I will try and take breaks for you to write down a question or two after each section as well. So let's jump in. So Julia is a programming language that by most people's standards is fairly new. The initial release was in 2012. And for context, the initial release of Python was 1992, I believe. So it's 20 years younger. And importantly, the release of version 1.0 of Julia, which means stability and continuity, happened in 2018. And so since then, the language has really kind of exploded in its use. This is an open source language by very high standards, in fact. It's general purpose and it has a very modern design, partly because it's recent. So it's benefited from lessons learned through the development of previous languages. And in fact, it is one of its strengths is that it interacts very well with, say, Python and Jupyter and things like that. So once you're familiar with this, you know, you come into Julia and it's not a huge learning curve. And you can reuse your codes from other languages as well. There is a rich ecosystem of packages that support different functionalities, like simple ones like plotting and reading files and data, which I will tell you about today, but also simulation and real like high performance calculation, supports GPUs, stuff like that. And all of this relies on a wide developer community that is distributed across the globe, with a lot of people in Europe, in the US, as well as in a lot of other places in the world. Involves academics, but not just academics. There are real software people that develop some of the contents as well. And so one of the things I would highlight is that, in a sense, Julia was designed to solve this so-called two-language problem, which you might have experienced if you do scientific calculation. That is, you want something like Python or MATLAB to kind of prototype quickly and demonstrate and share with colleagues. So kind of a high-level view into your science, but you also need often when you are doing big computations, a compiled language, like something like Fortran or C++ that goes very fast. And so Julia achieves both at the same time, which means that ultimately, if you wanted to use just Julia, you can do that and achieve both the performance and the high-level interaction with the language. So this will come clear, hopefully, with looking at some notebooks and some examples. But I would say, to me, in my opinion, Julia is a really good fit for this kind of community interested in scientific computation and communication. And another reason I use it is it's actually fun and very efficient developing in Julia. So I've migrated myself from a lot of Fortran and MATLAB in the past, and at this point I'm really focused on Julia because it's very rewarding, I found. These are my opinions, but here's a couple of links that you can visit where you will see a more representative set of experiences. In this first link, this was a blog post where a lot of people contributed their own little blurb explaining why they use Julia at this stage in 2022. And then the original motivation behind Julia is well explained into this famous blog post from 2012 that was the initial release. So I'll let you read that at your own convenience. And moving on, here is the Julia website. So we're going to go there right away. The QR code should point you to the same website that I'm going to click the link from. And here we are. So this is the main web page where you will go to download and learn about Julia. So the download, for example, is a very simple operation depending on your machine. You just click on the right link and off you go. The documentation is extensive. I'm not going to walk you through all of that. I'll highlight the 40 plus thousand stars on GitHub that the language has received, which is an illustration of how popular it is. These are some of the same aspects that I've mentioned before, listed here, highlighted. But I just wanted to show you this one. So here, this link will let you try Julia in your web browser without installing anything. So you end up with a page like this, and you click the arrow. And this is a very simple way for you to try out very basic Julia things. Nothing particular here. I'm going to move on from this, but this is an easy way to get going if you want to try it out. There's a bunch more explanations in this page, a lot of very useful resources, but I'm not going to go through any of that. The most important thing is this is where you get Julia, and this is the central web page. Go back to my presentation. So we're going to look in a minute at a notebook that was designed to get people up to speed with some of the language, the Julia language, basic features. This was contributed by Lazaro in the context of this Julia for Earth observation workshop that we have organized in January, and I will come back to this later. Again, the QR code should send you to the adequate notebook. And on the left, you have the view that you would get of the notebook. This is a Jupyter notebook from within a Jupyter lab instance. This is a computational environment that is quite friendly and common. You will come back to this in other sessions. For example, Python uses the same. And I'm going to show you more of this in a second, but I'll make a slight detour to tell you about this web page. So this is a web page that has a list of the notebooks that we're going to be using today, and it also provides the environment that I just showed you in a portable fashion, something that you can use yourself. So I'm going to just go to this web page. This is from the Julia Climate organization on GitHub, and you will see that there's a menu that tells you about notebooks of different things. What I want to show you today is just the directions, which have to do with how you get back to us with questions after this seminar, or how you run notebooks in various ways. So if you have your own sort of installation of Julia, then you can follow this step by step. This is to start a Pluto notebook framework. Here is a command line version of that, but what I wanted to get to is really this. So this is how you're going to run with the so-called Docker program on your own machine, the very same environment that I'm going to be using today. And it is available in the cloud with this free binder link. So I'm going to click on that. to show you. So you can try the notebooks here, the ones that I'm going to show you today. The caveat is that this is a little slow and it's not a very big computer, so it will run out of memory rather fast. So I'm not going to be using this one specifically. I'm going to let it proceed, and hopefully we'll start to show you what it should look like, but at the end you should have something that looks like this. Just double check, is it running? Okay. So this version here is on my laptop. But it's the same environment, and that's the beauty of this, in a way, is that you can have the same environment in the cloud on our own machine, and you can install it with Docker. In any event, you can also run the notebooks natively once you have installed Jupyter on your machine and Julia. So you don't need this, but it's an option that might be useful for you. So the interface, as you see here, has a bunch of buttons. And if you just click on this Julia 1.9.1, it will start a notebook, Jupyter notebook in this case, that will show you that you can just start using Julia. So if you again do just 1+1 to check that this is just running, you can then start doing more Julia things. And the first thing I'm going to show here, or really the only one, is the package manager. Which we're going to put this way. So this is how you import the package manager itself, which is called packaging. And then you can start looking at what is on your machine. In this case, this little container that I'm using through my laptop. So here you're seeing that this has a few different packages with versions and so on. And this is just an illustration of Julia working with packaging. So rather than looking more at this one, I will go to this notebook. This is the one that I was mentioning in my slide, the beginner's notebook. It has a lot of topics covered, which are summarized here. So it tells you about the syntax of the language, data structures, packaging, the package manager, which I've already told you about. And then things about tabular data and variable transformations. So we're not going to cover all of this, and we don't have the time for it. But I'm going to give you a hint of a couple things. So the native data structures, if I go further down, bear with me 1 second, I need to find it. Oh, this is already started, sorry. Right, native data structures. So these are data structures that are natively supported by the language. And the reason I wanted to highlight this part is there's a lot of things there that you're familiar with. For example, this first one here is a string, right? And so you define a string in Julia by just putting these double quotes and then text in between. If I add an extra cell here, I can, use it again. And I can do what's done here, which is to show you the type of it, things like that. And you can also index into a string. So if you do this, which is the indexing with square brackets, that's how it's done in Julia, and it starts from 1, not from 0, like in other languages sometimes. Then you get, a character. So these are strings. Tuples are sort of list of sorts. Name tuples are a particularly convenient version of that. Here you have a lot of different explanation in this notebook. So you will learn in detail how to use strings, tuples, which are kind of a list, like I said. So this is a tuple, so on and so forth. An array, maybe if I'm going to go to look at the array type, starts here. So an array or a vector is the same, except that an array is typically a multidimensional vector. And you can define them in different ways. So here is one way that you can define it. And so if I change this, it's going to make my vector longer. Similarly here, we can define it by putting values And so a lot of very simple things, basically. Sort of standard syntax that you will find in all languages. You can define arrays with predefined values like this, zeros. You change the size here, so on and so forth. So a lot of things that if you have used any other language before, you should be familiar with. And one more topic briefly before I move on. There is a very good support for more advanced types. One of them, for example, is what's called data frames. In Python, which you will hear about later, this will be pandas. So this is how you handle lists and tabular data. It then lets you read CSV files. And so, for example, here is a command where you just read a CSV file to get a nice formatted column in the data frame format. That then allows you to do a lot of things like look at columns with this nice syntax. So this is the table, so on and so forth. So there's a large suite of tools and functionalities that relate to tables and tabular data, which is a strength of the language. It's very well developed. So I think this was all that I was going to highlight from this notebook. So I've told you about this, and I've told you about the beginner's notebook. So before I jump into the next section, I will take a little 1-minute break to give you time to write questions that you might not have written yet. All right, I see a lot of great questions on my screen. We'll get to them at the end, I believe. So with this, I'm going to move on to the next part. We're going to talk about ocean color and how to use it in Julia. Specifically, I'm going to show you 2 notebooks. One will be on deriving chlorophyll from reflectance variables, a topic that has been covered from the theory side in previous lectures. And then the second notebook in this part will deal with the classification of ocean color data, also a topic that you should be familiar with at this stage. We are going to be using the oceancolordata.jl package, which is somewhat depicted here on the left. It contains a small package that contains the functions that implement what we are going to be talking about. For example, the last one converts from remotely sensed reflectances to chlorophyll A. It's part of a Julia Ocean organization that you will find on GitHub. The link is at the bottom of this page. And what you see on the right-hand side is a list of some of the packages that are in this organization. So you see that ocean color data is there. Argo data, in fact, I have moved to a different organization, but deal with Argo data, as the name indicates, and other things that might look rather relevant to this, like the 2 at the top, to this topic we're talking about today, but from the modeling side. So 2 different kind of models for marine biological cycles. That's the first one, ibex gel, and plankton individual gel is a agent-based model that represents phytoplankton populations. I am not going to touch on those today. We're going to focus on ocean color data. The first notebook for this part is this one. You have a snapshot of some of the text on the left and a QR code that will lead you to a rendering of this notebook online. It is found in the Marine Ecosystem Notebooks folders, repository, as it is called, within Julia Ocean. And we're going to jump right into it. So this is the one we were doing before. So we're going to switch to this notebook now. So this notebook, as before, is running in Julia. This is, again, a Jupyter notebook. This first line here is an important one, so I'm going to explain. You will find something like this in pretty much every Julia notebook. This is a line that says we're going to use a certain number of packages. And so before I've shown you the import approach, using is kind of similar. It's slightly more common. So here we are using the ocean color data JL package. And then we're going to use the plots package, for example, to make graphs from our results. This notebook is looking at ocean color data from the perspective of comparing it with models and comparing it with variables that reflect the amount of irradiance coming back from the sea surface, but that's the sun irradiance. So it's a slightly different variable than the one observed. So we're going to go through a couple of steps of conversions to get to this set of variables, which are called irradiance reflectances. And they're going to be defined on a certain set of wavelength, 13 of them here. We're going to convert those to remotely sensed reflectances, which you've heard of in previous lectures, that are on these wavelengths. So this means we're going to do, as you proceed to the notebook, you're going to do an interpolation, a conversion, which is this formula here, to go from the irradiance reflectances to the remotely sensed reflectances, and then interpolate in wavelength space. And here, what I'm showing you now is sort of the verification of the result. So the fact is we have this red curve that is, I think in the horizontal axis is just the wavelength. Should have indicated that, sorry for this. In the vertical axis, you are going to have the RS. That's the reference we got from our colleagues at PML. And then this is the result that you get in green with the function that's provided by the ocean color data JL package. So all of this to say, this is working. You can use the package to do this. The next part of this notebook is going to be now the set of formulas that get you from the remotely sensed reflectance to chlorophyll, which is defined as a ratio, as you know, between the bioratio between the blue and green values of reflectance. There are several different algorithms that have been proposed to do the conversion beyond that point, which involves this polynomial here. So this gives me a quick opportunity to walk you through an important feature of Julia, which is how you operate function element-wise. Here you have a vector. If I show you this, it should be a vector. It's in fact just one value. And then this one is also just one value, but they are in fact vectors. So this operation is going to take the log of the ratio of those two values. And the dot here means that we're going to do operation element-wise, which is practical. And more clearly, we're going to see it here, where this is going to take well, you're going to see the same thing here. So we put the dot basically so that we can operate the operations exponential here in this case on every element, even if there's only one. By the end of this, we have chlorophyll. So through the change of variables and then the sequence of recipes, we derive chlorophyll. At this point, the notebook continues to tell you about classifiers, but we're going to do this in a separate notebook that is slightly more visual. So this one here is going to take remotely sensed reflectances as an input. In fact, we're going to get it directly from the OCCCI dataset. We're going to have it on 6 wavelength, and then we're going to apply a couple more operations to that to create the classifier or to apply the classifier. As before, we have a set of notebooks that are being used. So the first two you recognize, ocean color data and plots for visualizing. The new one is NC datasets. And so that is a package with which you're going to be able to open and manipulate NetCDF datasets, which is a very common file format that you will have heard about in previous sessions, and you'll hear about it again in the coming ones. So every programming language has ways to deal with these files, read them, write them, etc. NC datasets.jl is one of the Julia packages that does this for us. We're going to see how it is used. The optical classification in our case is going to be one that was defined by Moore originally, and that was extended later on by Tom Jackson and colleagues, some of you here. It proceeds with a vector and a matrix that we read from files. So at this point, we have our classifier ready to be applied, and we're going to read in data sets to apply. So this is the illustration of opening a NetCDF file and using it. This little NetCDF file contains a bunch of variables. The command that you see here opens the file and creates a data structure DS, which is a lazy representation of what's in the file. So just the metadata, that's what lazy means in this context. So if I use the next cell to show you, this is what the data structure looks like. So once you just open the file this way, you are able to see what's in it. And you see, for example, that this surface reflectance is at a certain wavelength and is stored in an array with certain dimensions indicated here. It has units and so on. So you have access to all of those things immediately as soon as you open the file, but opening the file itself is very fast because you're actually not reading any of the data itself. The next lines in this cell here are going to start accessing variables. But the first step is also lazy. So that is, if I show you this data structure now, it's also just metadata. So now we're accessing the variable called RRS underscore 412 in the file, but we are just for now retrieving the metadata. So again, you get all of the information, but the data has not been accessed yet. To access the data is with this syntax. Now is when we're actually retrieving all of this data to memory, and you recognize the size of the array that was announced by looking at the metadata. And a lot of the values here are missing, but you start seeing numerical values that are the observations. So by this point, we have all of our variables in this kind of lazy format, lazy form, and then we can proceed in using it. So as I said, we're going to here extract one array from the file, and we're going to plot it. So here I wanted to show you the use of the plots package to produce a heat map. So very simple, you provide the 3 variables in the title, and here you go. If we keep going in this notebook, is where things become slightly more interesting in a way. We are going to see this first little code block is just going to be to select the points that are not missing. And then this is the application of the classifier in this second block here. So a couple of things to know. One is, this is a loop, standard way of writing loops. You have other methods to do this, but this is the simplest way to write a loop. Should feel familiar. And then here we're getting an index. We're then going to form a vector of values that we're going to provide to this fuzzy classification function with the pieces we read from the file that defines the classifier before. And so at the end of this loop, we now have a map of the membership for each of the classes, which we can plot. And so again, we're just now getting the right variable in the right format for plotting, and then we can just depict that. So very simple, should feel familiar. And that was the end of what I wanted to say with this notebook. So let me go back to the presentation. Let's see. So we've gone through the I saw a question about the link. There will be the link to the presentation at the very end of the presentation. This was the notebook, 2 notebooks, one that derived chlorophyll from reflectances, another one that derive classes, classification from the same kind of data. And that concludes this part. So again, I will take a little break to give you a minute to write down questions you might have. All right. So let's move on to the next part of the presentation, the last main part. Now I'm going to tell you about this workshop that happened in January, where we brought together a big part of the community that develops Julia tools for Earth observation, broadly speaking. We're going to look at 2 notebooks. One has to do with different kind of data sets that people use and combine that are the kind of array types, which here we're going to call rasters, and polygons, which delimit regions. So we're going to do this, and then in the next, the last notebook, we will look at another classification problem where we're going to use a random forest toolbox, something that you might be familiar with as well. So Julia AO was a first of its kind workshop where we brought together, as I said, a lot of the developers of packages that have to do with file formats, applications, graphics, AI, that kind of collectively are useful for understanding and interpreting Earth observations, as well as models, in fact. And so here I'm not going to tell you everything that's happened in this 1 week event, but there was a lot of notebooks that you will be able to access there, and that will give you potentially a lot of useful examples for different tasks and different goals. And I'm just going to take a few examples. I will click on the web page just to show you this. Again, the QR code should lead you to the same web page I'm about to show you on the screen. And so what you will find here is a lot of useful information about the contributors that participated in this event. I'm not going to go through everybody's bio, but we were about 20. The program involved 5 days of lectures and hands-on session. I'm just going to go to show you briefly. You see the names of the contributors, and then you can refer back to this page later. I'm just going to show you the breadth of what's there by scrolling to the page. If I go back to the top, you have a few other things. So this is the GitHub repository. There's also a place where you will find data sets we used, and then an explanation on how to use Docker, which I mentioned at the beginning, with a video of how to use that. The GitHub repository itself, this is what it looks like, and maybe the first GitHub repository that I showed today. So this one is under the Air Center, which was the lead partner and sponsor for this event. And the notebooks, this looks like a little folder. Go in and you're going to find all of the notebooks for each of the sessions. And I'm going to select a few of them today to show you examples. And go back to, I guess, my presentations for just 1 minute. We're going to look at two cases, two aspects. So one has to do with gridded data and polygons. So here is a first notebook example. This one was using data from the CMEMS platform and the Earth data platform. So we just extracted, for the sake of this notebook, a little subset, which is the gridded fields you see here, that show the colors, that show sea level anomaly in the colors, and then in the contours, that's where the polygon comes in. You see the ocean topography. And so this notebook was just take this time series and generate a little movie animation from it. Here is another way that you might have come across polygons and arrays. Here you see the so-called Longhurst provinces. So this is a shapefile originally that we just read in with the package and then display. But you see that the colors, could be analogous to an array and to a kind of a. So so we're going to go deeper into this topic. Not with this particular notebooks. We're going to use this one, which was contributed by the lead developer of this package, rastersgl, and handles the same things, this kind of complementarity of arrays and polygon data sets. And we're going to look at how to convert one into another. So again, the link on the right side should give you the notebook itself. What I am going to do is I'm going to go back to my environment here. This is, for those who have missed at the beginning, this is kind of a standard Jupyter Hub, Jupyter Lab, in fact, instance that I'm using, that you have available to you as well, and that can be used to run the notebooks. So we've looked at so far notebooks like these, which are of the Jupyter type. We're going to look at a slightly different framework now, which is here and is called Pluto. So to get back one step, here is the landing page that you get in the Jupyter Lab. If you click on this Pluto link, it opens this page, and I am going to be looking at this particular notebook. There are important differences between Jupyter and Pluto. One of them is that here the codes are typically hidden by default. So these are actually code blocks, markdown cells that are rendered, or actual code block like this. They can be hidden or highlighted. Also, the order of the operation does not matter in the rendering of the notebook. And it is finally a reactive framework, which is maybe the most important difference, which means every time you click somewhere in the notebook and you change something, everything else that depends on it will adjust. Moving on, going back to the notebook at hand, this is going to be looking at raster.jl, which, as explained here, is a package that builds on a lot of other ones to handle different data sets. So it has, in fact, as a dependency, NC datasets that is from LCDF. It will have ArchGDAL, which is for other types of datasets. And all of this is going to be used by raster.jl as a front end. You have an example of a dataset here that's been loaded with this, loaded to memory with this package. And so these are, I think, classes of vegetation shown as a function of location in terms of some kind of concentration. We are not going to go through the whole notebook because it is long. You can click on the right-hand side and we're going to get to the different sections. What I want to highlight is this part on the rasterization. So this is the sort of operations that you might be interested in doing if you're looking at satellite data. For example, get some kind of polygon defining a region, and then you may want to do statistics over your gridded data set just for that region. So you need to go between arrays and polygons. So this is what's going to happen here. We're going to start with a shapefile, which is defining the border of different countries. We're going to just read that into memory. This is what these first few cells are doing. And I'm just going to highlight this one here, which is you provide the file name. Then there is a package called shapefile that's going to handle the reading of that file. And then we pass that to the data frame package. All of this is on one command and gives you at the end a nice table where each of the polygons for all of the countries are in just one column. So they are very easy to access after that. These next commands are a little abstract, but what they do is they filter the table for just Indonesia. And so at the end of this, we have in this variable called Indonesia border, a polygon that represents that particular country. As you see here, plotting it is very simple because there is a method that's been provided to do this by the developers of probably the shapefile package. Now we have the polygon, okay? We're going to do what's called rasterizing it, which means looking for an array where the inside of the polygon is going to be of one value and then the outside is going to be on the other value. This is very, very simple to do with the raster.jl package. It comes down to one command, which is here. Just say rasterize your polygon, and then you have a little bit of explanation to give as to the missing values. And there you go. Now you have this color map because we're plotting the result of this rasterization with a certain color map. And everything is either 0 or 1. And you get in yellow the blueprint, the footprint of the polygon. And so you can verify this by putting the polygon on top of the array that was plotted just before, and now you have gone from polygon to raster, which means array. Here's the kind of applications that you might want to do with this. Going just one step further, here we're going to look at Denmark, Sweden, and Norway. Same thing as before. We're going to get a data set that's going to be the climate of this of the world for certain variables. So this is what's shown here. These are your different variables. So there's minimum of temperature and maximum of temperature, I believe, and then precipitation and winds. We're going to zoom in on one of them. Here we're just looking at the minimum of temperature. And then there is this mass function, essentially where all of the magic happens. Now we are just providing the variables for the climate, the border of the country that we want, and in return we are going to get a masked out version of that. So the plot, as is obvious here, doesn't always come out great. This is pretty much white, but the reason is that Denmark is a small country and we don't want to plot it just on the global map. So there's a function to take care of that, which is trim. So once you do trim, then you get to what you're looking for, which is the climate for all of those variables in the particular country that you're interested in. And so this happened, if you noticed, with just a few comments and an illustration of how the packages that you get will make your life very easy when they are well developed, like this WestRGL package. So now we're looking at Norway, and then we're going to see Sweden. So that's it for this notebook. I have one more, and then we will go to questions. This one is going to be using the same kind of data, typically images, data that are in format like TIFF, for example. We can take a bunch of images and ask the question, what kind of landscape is this? What kind of vegetation might it be? And so to do this, you want an algorithm that's going to take images and give you classifier, a membership for certain types of landscape. So this first example, which we won't go into in the details, uses WestRGL and then FluxGL, which is another package for neural networks. And then it generates a classifier based on a convolutional neural network. And I will let you explore this one. I will spend more time with this one, which has similar goals, similar kind of inputs, just uses something slightly different for the classification, and that is a random forest algorithm. So as per usual, you have the QR code to the notebook on the left, and I'm going to, on the other hand, go to the live notebook, which I believe I have here open in Pluto. Oops. I go back to here, I'm back to Pluto, the main page, and I'm going to choose this notebook. So in this notebook, I'm going to go a little quick, again, as before, to just give you the flavor of what's going on. And so one thing we haven't really, well, we have mentioned briefly is how you get data files into memory from this so-called CSV format. So we are going to look at reading these files. I'll show you the command to train the model and then some of the output. So again, very simple to read a file. That's one thing we really want to do often. So there has been a lot of emphasis on doing that right. Here, this is a CSV file. So you just provide the name and then this command is going to turn into a data frame. Boom. Now you have a nice array version of your data. So this gives us the training and the test data set. There's going to be a bit of formatting going on here and setting up some of the methods parameters. And then here we are. We're just going to create the classifier. This is from the decision tree package. And oh, somebody can actually. Hopefully everybody else can. This is the one command that's going to build the classifier. And so then once you have this, you can start looking at how well it performs. In this case, we have 6 classes that we are trying to identify in the data set. And this is the training phase. So the verification that the algorithm works as expected lies in the fact that this matrix is going to be diagonal, which is called the confusion matrix. So we're counting, the diagonal is basically everything that was properly counted, properly classified. Once we've gone through the classification training, then that can be applied. And so now we proceed and we're going to read in data in the diff format, I believe. And then once we have this in memory, we can then just apply the classification. For some reason, my notebook did not do the plotting right here, so I need to figure that out later. But the end result is exactly what I was showing you on the notebook. I'm going back here. And so the end result of this is on the left, you have the input data, which is the raster of the remotely sensed reflectance, I believe, depicted in some way on the left. And then on the right is the classification that results. And so you see, for example, that very distinct areas emerge, like this one on the left, which is the outflow of a river, which I believe corresponds to the class where there's a lot of sediments. So this is a quick overview of the type of methods that you can today use in Julia without much trouble. There's fairly mature software to do all of these things that you might have come across in your research. I'll just take a brief moment to let you write your last questions, and then I'll wrap up. All right. So to summarize very simply, I'm going to just reuse this slide. I've shown you a little bit of an introduction to this language called Julia and some examples that demonstrate that it provides within the broad ecosystem of Julia software a lot of the functionalities that you may need for analyzing and processing Earth observation. I've given you a set of notebooks that you will be able to reuse on your machine or on the cloud that looked at ocean color. This was the first set of notebooks, and then Earth observation more generally in the second set of notebooks. At this point, I will close the presentation by just showing you the link to the slides in case you have you want to access them. The slides will give you all of the other web links and information that I tried to provide today. And on this note, I will thank you for your attention, and I will welcome any question you might have. Thank you.